Gestra, an international manufacturer of valves and control technology, commissioned the world's first complete glass steam system in 2009. For the first time ever, it's now possible to look right into a steam generator and see how steam bubbles arise, how feed water is deaerated, and how the various types of steam traps really work. A number of videos take a look at important facets of the steam condensate system and its operation, thermodynamic processes taking place in the generation of steam, as well as during condensation, condensate discharge, and the origination of the water hammer effect are shown in a way that's easy to understand. This video looks at condensate discharge using various kinds of steam traps, as demonstrated in the glass steam system of Gestra AG, Bremie. The steam system consists of a secondary steam generator with a service pressure of 1.3 bar G, corresponding to a saturation temperature of 124.7 degrees centigrade. The capacity of the steam boiler is 50 kilowatts, which yields a steam flow rate of 80 kilograms per hour. As the condenser, we are using a glass heat exchanger mounted above the steam generator. Cooling water flows in the tubes, while steam flows in the jacket around the tubes. After passing through the steam traps, the condensate is collected in a glass condensate tank at normal atmospheric pressure. In this film clip, the origin and effect of thermal pressure pulses, generally known as water hammer, will be demonstrated. For this, steam is introduced into a horizontal glass tube with a slight upward inclination, thus forming a pocket of water. The water enclosed in the tube on the left-hand side is cold, whereas steam is available on the right-hand side. This represents a typical startup situation for pipe segments with poor drainage. The steam valve is now opened slowly. First of all, one or two air bubbles flow to the left. After a short while, the water has been warmed up slightly. Now the first steam bubbles are seen flowing through the water. These bubbles release their heat suddenly and condense into water. The water attempts to fill this vacuum as quickly as possible, collapsing into the empty space. The water quantities accelerated in this way must now be stopped in fractions of a second. It's possible for pressure shocks with peak values of more than 1000 bar to be created. This becomes noticeable through the visible shocks and explosive sounds. The shutoff valve must be opened very slowly to ensure that the number of steam bubbles passing into the water is kept as low as possible. Once the entire body of water has warmed up to boiling point, the steam bubbles condense at only a very slow rate. There is then no longer any danger of water hammer. The experiment is repeated a second time. This time, however, this part of the horizontal tube is arranged to have a slight drop towards a siphon. Having the siphon downstream ensures that there is always a steam bubble in the horizontal part, and the water flows along the bottom. Through their volume, the steam bubbles at the top of the tube form a buffer space, which minimizes the water hammer at startup and allows the startup process to be initiated faster and with less risk. Once again, the valve is first opened slowly. After the water has warmed up a little, it can be seen that a vapor phase is created at the top of the tube. Now the valve can be opened more quickly. The strength of the water hammer is much lower than in the previous experiment. For this reason, Gestra recommends the use of the condensate dampening pot type ED for condensate lines where the pipework changes from the horizontal to the vertical orientation. Thank you for watching.